Hello. 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 Okay. Hello. Good afternoon. Oh, that's two of you. Thank you. Good afternoon. I'm going to say this in order. Oh, good afternoon. Awesome. Hello, Jamie. Good afternoon, Carla. Good afternoon, Michael. Awesome. Thank you. Wait, do I even see? Yes, I do. Okay. And and good afternoon, Montserrat. Good afternoon, Amelie. I did it again. Okay. Yes. Good afternoon. Wait, and there's an interruption. And good afternoon, Mira. I do see. Hold on one second. Sorry, we're coming. Okay, one second. Okay. Um. Okay. Good and good afternoon. Oh, and I mean Tiggy is here. Okay. Let's get started. Let's get this party started. Um. Okay. Okay. Hello, Tiggy. Good to see you. She wins the video award for today. And by the way, for the moment, I mean, there's still time. And you know, it came up in the other class. Soon I'm going to open a portal to really get them take multiplayer co-op to a new level. We're going to open a portal soon for the day everybody goes video, even for one like beat. If we can get, so this is like weird reverse peer pressure. If we could do a day, if I'm going to open a portal where if everybody goes video, even for a moment, it'll be like such a preposterous number of points that we'll need scientific notation to calculate or something like that. Like, anyway, whatever. That's a new, because it almost happened in another class and I was shocked. Now, of course, it was because like half of the group was, it turned out was all sitting at the same table in in a lab or something doing class, which is a good way to do this class. Anyway, all right. So we have to get rolling. Tiggy is our only video star for the moment. But she'll carry the lot. I mean, and I know Mira's here. Okay, yeah. Oh, here she. I knew it. I knew it. Thank you. Sorry, that was totally okay. And it doesn't have to last, but I just all right. Something was just there was a missing piece inside me. Okay, I shouldn't do that. But all right, now class can start. Okay, I'm totally kidding. Except I'm not at all. Okay. Oh, and thank you. Here comes Angela. Thank you. Okay, but I will. Another professor, actually, like someone that you all know very well. I was having a meeting with him. He shall remain nameless, or she, but it's he. And he goes, by the way, I love your class videos. He said that to me. And I said, wait, really? Wait, what? Wait, first of all, you've seen them. And second of all, wait, what? And he seemed like he was being really sincere. He's like, no, I mean, I haven't seen a ton of them, but no, it's really great what you do in class or something like that. And I still didn't really, it was just, and I said, wait, that's really nice of you. Really? I mean, the ones of course you haven't seen all of them, but the ones you've seen, you really like? And then he goes, okay, I'll be really honest. He goes, I think I really like them. I think I really like the tone, but I kind of like, I tried to watch them, but I could never get through the part where you're saying hello to everybody. I always turn it off before you ever get to any physics. You're always just saying hello to everybody. And he's like, but it seems like by the time you would get to physics, it would be really cool. Right. So I learned a lot from that discussion. So we're going to get to physics now. Okay. I don't know who triple OG. That's quite. Or okay, here's the deal. We got to do some physics today. We have a plan, as much as it won't look like that. I have to ask you a couple of questions first. You didn't, because you didn't have lab today this week. I understand that. So just remind me a couple logistical things. In lab last Tuesday, last week, that was a lab that you made the wave animations, correct? Hello, Ali Rat. Good to see you. Thank you. Hello. And did Tiggy just nod, or did Mira just not? That was correct that you made the wave animation? Okay. And is this also correct? I'm not assuming that you've seen one video from me. Maybe it was a week before that. Then you've seen me talk about a collection of phase staggered oscillators creating a wave, right? Like, I'm not assuming that you've mastered that or that it's totally clear, but am I right that this concept has come up in our discussions where if you put a bunch of oscillators next to each other, that is what creates a wave? Am I saying something that's even remote? That's a sort of yes, Mira? Okay.
Yeah.
Oh, that's a total yes. Oh, by the way, I mean, if there was well, anyway, she's getting a lot of points. I'm just saying. Okay. Okay. Good. Now, so that's where my head is right now. We've in my head to everybody, we have finally transitioned in this as a class. We spent a lot of time on harmonic oscillation and all these cosines and sines and radians. Like, we accidentally had two homework assignments that were like sort of annoyingly similar to each other. I realized that it was sort of an accident, but you've been doing all these cosines and radians like a lot. And I'm sure and hopefully they're sort of clear to most people, but I know they're very boring at this point to probably everybody. I'm going to remind you now that the reason we've been spending all this time on single oscillators, the real point of all of that is our belief that if we take a bunch of oscillators, of harmonic oscillators, and we line them up and we assemble them in a certain very specific way, and by we, I either mean human beings, physicists, or Mother Nature, like if a huge bunch of harmonic oscillators are arranged in a highly specific way, the resulting motion is wave motion. In fact, let me just make, in other words, well, I'll say this on the next page. Hold on a second. Okay. Okay, one thing I just want to make clear and we have logistical, like I said, there's like logistical things that we have to deal with in the class and so forth, but I just want to make clear right now where we are in the class material, especially because, well, whatever, I want to make clear where we are in the class material. This whole class is ultimately supposed to be about unthingy motion. Obviously, that's not a real scientific word, unthingy, but I think it communicates something. What you studied in Physics 101 and in certain other prior physics classes, you studied thingy motion. You studied the motion of actual things through time and space. In scientific terms, what you studied in Physics 101 was the trajectories of particles. Whether those particles were tennis balls or bullets or planets or electrons, like it doesn't matter how big or small they were, you were studying how a discrete, bounded, countable, identifiable, material object of some kind was going from here to there in space, right? That's what you were studying in 101. And honestly, in a way, you were studying for like the first month of this class, or reviewing or unpacking or whatever. But the goal of all of that, where this whole ship has been heading, is that this class ultimately is supposed to still be about motion through time and space, yes, but we're supposed to be ultimately trying to understand in this class, in scientific and mathematical terms, how certain motions through time and space don't involve particles. We're here to study how something can move through time and space without actually being a thing, right? Without being a thingy thing. What that's a little bit abstract to get our minds around. To remind you again, like to go back from like the first day or whatever, when I refer to an unthingy motion or the sign, I'm referring to motion through time and space that does not involve individual material particles. In fact, I mean, there's a lot of different ways I could say this. I mean, perhaps, just perhaps the most vivid way I can say what I'm saying is when I say unthingy motion, I think that what I really mean is immaterial motion. Someone's here. When I say unthingy motion, I mean motion, a real, scientific, observable, reproducible, analyzable, predictable motion from one point in time and space to another point in time and space. However, I mean motion that doesn't involve any kind of material object that you could ever like separate or identify and say, oh, there's a baseball or there's an electron or there's a planet or whatever. Rather than that, that would be called particle motion. That would be what you did in Physics 101. We're here ultimately to talk about when something moves from A to B, from point A to point B, something moves, some motion is observed and analyzed and calculated and all that, but there's no object that we can actually say is making the journey from point A to point B. And you see, I get tongue-tied the more I talk about it. The more I talk about it, in a way, the harder it is to even say what I'm saying. But the specific example that we have now arrived at in class, or you arrived last week in lab, or we started to arrive in the video, the example that we arrived at, the first example of immaterial motion, of unthingy motion, of the flow of information rather than the trajectory of a particle. The first example is wave motion. Let me be very clear, or let me try to be very clear on the next page. Oh, sorry. Oh, I know people are in the waiting room. Sorry. Hello, why is it not working? Wait, I know people are in the waiting room. Oh, okay. Okay. I'll keep going. Okay. Um, okay. This is like, in a way, really obvious, maybe, sort of, but in a way, totally not. And I think it needs to be super explicit. Because from here on and for a while, we're going to be talking about waves. Okay, we're all about waves now, and waves are like the centerpiece of this class. Everything you did, all the math of cosines and radians and individual metal springs going back and forth, oscillating back and forth, or little individual pendulums all oscillating back and forth, all of that, whether it was interesting or new or not or dry, all of that was an ingredient. Harmonic oscillation is an ingredient. Every one of those oscillators you were looking at was a particle going back and forth through space and time in a classical physics way. Like hopefully we learned some new math of how to describe it or whatever. I mean, that was the goal. But when you look at one individual mass on a spring going back and forth, or one individual ball on a string, i.e. a pendulum, swinging back and forth, you're looking at a particle moving back and forth in space. But the purpose of all of that, is that it was to put a bunch of harmonic oscillators together in a very specific fashion and construct something that we call a wave or a wave pulse. And the thing about waves that I want to make really clear in English before we go on. Oh, sorry. And I see there's things in the chat. I'm sorry. Wait, there's things in the chat. Oh, good afternoon. Good. Oh, hello. Good afternoon. Okay. The thing I want to make clear about waves, like everybody, of course, everybody like vaguely, everybody recognizes a wave when they see one and everybody knows the word, but like what is really going on with a wave? What is the big deal of waves? Why do they fit in a physics class and yet fit late in a physics class? If you take the example from lab 3 now, right, of just an example of two people in a room holding a long stretched coil of metal, that long slinky thing, and stop me if you didn't do this in lab 3, but I think you did. So that's a bad drawing. But if one person shakes one end of the spring and sends a pulse from one end, from point A to the other end, point B. Okay, forget it. If one person, if a wave pulse is sent from point A to point B, the thing about it that makes it that's so special and so worth studying is that something clearly went from point A to point B. Like it's not an optical illusion or something like that. If you see a crest or you see a trough or you see a bump in the spring and you follow it with your eye as that bump, that ripple flows, propagates from person A all the way to person B, you're not kidding yourself. Something really did go from person A to point to person B. And let's be more clear. It's not just that something sort of vaguely was observed to move, but something moved in such a specific, reproducible way, like you can do it again and again and again. You can do it at will. You can make it happen. But we can put numbers to it, right? Like someone can literally say, okay, and I think you did sort of in lab A, or to a certain extent, you can say, okay, person A and person B are standing 5 meters apart, like you could put meter sticks between them. You could start a stopwatch the minute a bump or crest or trough starts flowing from person A and flows to person B. You could stop the stopwatch when the crest or the trough gets to person B. So you can literally say something like, aha, it was 5 meters of travel and it did it in 10 seconds. So this bump was going at a velocity or speed of 0.5 meters per second, right? Like you can do all kinds of physics calculations on the bump that you observe traveling with your eye, and you can rely on those calculations to the point of making a prediction, right? You could say, okay, now you stand farther back, and I bet you it'll take, if you stand this many meters farther back, if you stand 20 more meters farther than you were, then I think it's going to take another 10 seconds or whatever. I forget my numbers already, but you can predict how much time it's going to take for the bump to get to the new location, because you can plug into old physics equations and you'll be right. Will you be perfectly right? Well, you won't be perfectly right, but you wouldn't be perfectly right with a baseball either. You'll be just as right as you would be if someone threw a baseball across the lab. What I'm trying to say so far is that when we observe a wave pulse travel through space, we're absolutely observing something real and something that we can make measurements on and we can reproduce, and then we can make predictions about later on. It's totally a motion that's within the province of physics, of science, right? But here's the big but. All that ever moved during this, say, this process of a long metal spring being stretched in the lab, all that ever did any motion at all was metal, right? You're all holding this long coil of metal, and it's shaking up and down and shaking up and down, and metal ripples is what you're seeing flow back and forth. All that's ever doing any motion at all is metal, right? In this case, of course, if it was a sound wave, what would be moving would be air or something. But I mean, in this case, of this example, all that's moving is metal. And yet the key point is the point in black at the bottom of the page. The key point is that when you send good afternoon. When you send wave pulses through a long slinky made of metal, all that ever moves is metal, yet no individual piece of metal ever makes a journey from A to B. This is a key point. I'm going to say it again. I'm going to speak loudly so we make sure that what I'm saying is important. And I'm not saying something mathematical. I'm saying something in English. I'm saying that the hallmark characteristic of wave motion, the thing that makes wave motion interesting, is that it is real motion from here to there, but no individual object, no particle, no identifiable or countable or material object actually makes the journey from here to there, right? I mean, that's a big point. And that's exactly what we mean whenever we say waves, or we recognize them in our eye. If you're at the ocean, if you're at Coney Island or something, you're Far Rockaway or something, and you see, and you just casually like, oh, look at the waves coming into the sand, like as I'm standing here, or with my surfboard or whatever. Or even if you're just like whatever at a pond and someone drops a rock and you see the ripples flowing through the pond. It's totally casual, everyday occurrence, right? But please understand that what you're noticing with your eye, when you see these ripples moving across the surface of a pond, what you're seeing is water move. But when you say, and only water, nothing else. But when you say, look at that ripple go from there to there, there's no water that's actually going from there to there. Do you follow me? I mean, I'm going to stop. So that's some very strange kind of motion, that the only thing moving is water, but and something is moving from here to there, but no water is moving from here to there. I'm going to pause for a second. All I'm trying to do is just give you the conceptual recognition of what distinguishes wave motion from particle motion. I'm saying, just in English, that wave motion from here to there means a very real motion absolutely occurred from here to there, but no individual object, no piece of material or matter or mass in the world actually moved from here to there. Could you just raise your electronic hand if you're with me, if you get what I'm saying? Thank you, Carla. Thank you. She turned on her video to do that. That was okay. Thank you, Tiggy. I appreciate it. Thank you, Amelia. Thank you, XOOG. I don't even want to know who that is. Thank you, Roland. Thank you, Angela. All right. Thank you. Where's Mira? Okay, just kidding. Okay, thank you, Sadie. Okay, I'll see we get. Okay. There's Mira. Okay. I'm being really weird, but I would kind of like to know who the OOG is. I mean, just for safety's sake. I mean, it's hilarious. XC OOG. I'm into it, but Could maybe Triple OG identify him or herself in the, why am I guessing it's in the direct chat, just so we know it's not, I mean, I can't imagine who would ever join this class that doesn't belong here, but okay. Good afternoon, good afternoon. Okay. But yeah, soon, really, wait, I think it would be, I mean, for the sake of other people, please XT Triple OG, please tell me who you actually are in direct chat or something. I think it's kind of important. I see. Okay, but okay, you're on your phone. Yeah, but I don't know who me is. Could you? I see in the direct chat. Thank you, but could you say who me? That's. Oh, okay. Thank you. Got it. Okay. Fair enough. I'm gonna. Uh, it is someone safe, folks. It's someone we know. I'll just leave it at that. Okay. All right. So this is what wave motion is. So ultimately, what I'm saying is, when we talk about wave moving, we're not talking about objects moving. We're talking about information flowing. In fact, let me go a step further. All right. Okay. Okay. Well, I don't know what happened to the purple, but okay. Thank you. So Nathan, your hand is up. Is that to ask a question, or were you just responding to? Do you want to ask a question? I would be delighted. Or are you just responding from something before? So Nathan, okay, is you okay. All right. Okay, we're gonna get soon mathematical and stuff like that. But lesson that so point is you can't make a wave without a bunch of harmonic oscillators. The bunch of harmonic so and again, well, tell me if you want me to go back to this page, but just to remind you, I think we've said this a number of times. I'm not going to remind you. These are all identical harmonic oscillators. Okay. Right. Just to remind you again, and I'll move on a second. I'm depicting here a collection of phase staggered oscillators, right? Harmonic oscillators. Each one of these is the same harmonic oscillator, meaning has the same mass, has the same K, so it has the same angular frequency, each one square root of, for each one, omega is the square root of K over M, and each one has the same K and the same M. So each one is oscillating at the same rate in time, right? And so you set all up a huge, you or Mother Nature sets up a huge collection of all these oscillators, all say in a horizontal line, and leaves each one of them to be free to oscillate at its same rate in a vertical line, within a vertical neighborhood. But the one catch is that they're all set up at different phases, right? One starts right at the equilibrium position, then one starts at the amplitude position when the clock starts and they all start vibrating. One happens to be at the amplitude position, the next one happens to be at the equilibrium position, the next one happens to be at the negative amplitude position, and et cetera, et cetera. Each one is staggered in phase by a constant amount relative to the one next to it. And that constant amount that we're staggering them by phase, we call K, we call K being the angular wave number. K is measured. This is too light, I know. Well, K is measured in units of radians per meter. You can't read. Can you read? I think put in the chat if you can't read, if that's too light to read. But right, so K is some number of radians per meter. Say, for example, it's pi over 2 radians per meter. Remember, should I pause here and ask? No. Remember, pi over 2 means a quarter of a cycle, right? It's just as an example, right? Like, because 2 pi radians means a full cycle. So pi over 2 radians means like a quarter of a cycle. So if, for example, K is pi over 2 radians per meter, that means each one of these oscillators is a quarter of a cycle. For every meter that you look at this assembly, you add an additional quarter of a cycle to the phase of the oscillator that you're looking at, right? So the first oscillator just starts at the 0 position. The next one starts, so the 0th one starts at the 0th position. The first one starts at 1/4 of a cycle ahead of the 0th one. The second one starts at 2/4 of a cycle ahead of the 0th one. So K is that number of cycle portions per each meter. If you set up this whole situation and let them go, what you see is a ripple or a pulse propagate from left to right, right? No individual mass actually goes from left to right, but a ripple, a pulse, a shape goes from left to right. Excuse me. What I'm saying on the previous page is that from now on, that ripple, that distortion in shape, because that's really what you're seeing, right? You're not seeing an object move from left to right. You're seeing a shape of this collection. You're seeing a particular bump or a particular valley. You're noticing with your eyes, oh my God, those 3 are making like an upside down bowl or something like that. And then you're like, oh no, the bowl is over here right now. Oh no, the bowl is over there right now. What you're noticing with your eyes is the shape in which these pieces of material are assembled. So what I'm saying now, vocabulary wise, I'm saying from now on, that shape or that disturbance, from now on, that disturbance is called a pulse, okay? The piece of the wave that you track with your eyes that flows from one place to another is called a pulse. A pulse is not a thing. It's a disturbance or a distortion, a shape in a larger thing. And the larger thing, the larger collection of material particles that are oscillating harmonically, that larger shape is called, or that larger group of material is called the medium. Okay, so partly I'm just giving you vocabulary right now. From now on, a wave is not a thing that moves from here to there. It's a pulse that propagates through a medium. From now on, a wave equals a pulse propagating through a medium. The medium is the name for the vast collection of material particles that are oscillating in this phase staggered way. Okay. So we're all caring about the waves now. We analyze the oscillators to put them together to make these waves. And now, if each one of these oscillators is described by its own equation, the equation for harmonic oscillation that you've had coming out your ears for weeks and weeks, if each one of these is described by its own equation, and the only thing that's differing in all the equations is the phase constant, right? What we said a number of weeks ago is we could put all these equations together, we can capture the whole thing. We can put together the whole thing and say, and I know you've seen this before, this is partly review, on partly context, I don't know. This is the equation that captures the whole wave, right? It is y is now a function, y is a function of two independent variables, vertical position is a function of two variables, horizontal position excuse me, and time, also an independent variable. One dependent variable is being produced by two independent variables, right? In other words, to know how high the ripple is, you need to know two things. You need to know, where are you looking? Like, which ripple? Are you looking over here? Are you looking over here? Are you looking over there? And you need to know at what time are you looking. But if you specify the time and the horizontal place that you're examining this whole ongoing flow, then if you specify the horizontal position and the time, you can know what the vertical position is. There's a lot of in and out going on here. Hold on. Jeez. I really will try to not just be talking for this whole, I always say that, whatever. But there's a point I want to get to. When I get to that point, I'm going to turn it more to you guys. So be aware. This is the equation that captures the whole wave. I know you've seen this before. Hopefully I'm just giving it some context now, or putting into perspective, the context of the larger class. But this is the equation that captures the whole wave. But here's where I'm going with this now. Okay, I'm just writing. This is the equation. This is the equation to capture wave motion. Okay, but what does it mean? Remember, omega is angular frequency, right? Omega is how rapidly, how frequently each individual oscillator is completing cycles per time, right? It's this. Oh, well, for those people who are falling asleep, there's going to be a wake up in a minute. So my crazy son, one of my crazy sons, is about to come in. He will, of course, interrupt us until he disrupt everything in a minute. So I apologize in advance. And don't get me wrong, I love him like a son, but maybe not like a physics student. Hold on a second. Okay, omega describes the cycling rate of each oscillator. Also note, that's a triple equal sign. Like what it means is how many cycles it makes per period of time, right? Like the units of it, remember, are radians per second, right? And remember, a radian is just a 2 pi of a cycle. A rate, right? 2 pi radians makes up one cycle. A radian is a 2 pi, is a sixth of a cycle. Remember, capital T, if you want to write it to the margin, capital T is the amount of time for a full cycle. So when I say 2 pi over T, I'm saying how many cycles we make per every second, right? That's what omega refers to. Again, all of this review work and everything you've done, all this cosine work and stuff, is to like really make sure that we understand, we can picture what omega is about. Omega is just the rapidness with which one oscillator completes cycles. That's what omega is. That's what it means, triple equal sign. I'm going to remind you before I move on. That's what it means. But off to the side here, what it is, double equal sign, is K over M. Please stop me if this confuses you. Don't let this confuse. I mean, admit it if it confuses you, but I'm saying what it means is cycling rate. What determines it, we learned in the other videos and the other classes, what determines it, like for a harmonic oscillator, the frequency, the rate of oscillation in time is fully determined, remember, fully determined by the material parameters K and M, right? This is like a sidebar, but it's a crucial sidebar for where I'm about to go with this. And here we go. Hello. Can say hello quickly. That's very.
I no homework for the rest of this semester.
Okay, that's funny. That's good. Okay, you can't see them, but yeah, that's good. No, I'll try to take that seriously. I'll play when this class. Let's go play after the class. Okay.
Someone tell him what.
Madonna just said thank you for the no homework. Okay.
One more thing. Someone show him the happy cat dancing meme.
I don't want to see the happy cat dancing meme right now. Not right now.
Someone
Oh, that's Tiggy. Okay. Okay. Someone will show me the happy cat dancing meme.
Whoever does it first gets no homework for the rest of college.
Okay. Well, we don't have the authority over that, but all right. Well,
I don't care. I am the government.
Okay. All right. Government. I'll see you upstairs after the class. Thank you. Welcome home. Love you. Okay. Feel better. Feel good. Okay.
We'll be walking.
Yes. Okay. Okay. All right. That was okay. What else we have in the chat? He does mean it, but Okay. Oh, Carla thanks you also. Okay. Okay. Oh, he says, okay.
That you listen.
Okay. 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 Sorry. And I know I'm all over the, oh, and you, Chan, thanks. Okay. Okay. Thank you. Okay. I wish I could actually, enforce that. Okay, I'm trying to make a distinction. I've promised this is going somewhere. It feels like I'm just talking all over the place because I am, but this is going somewhere. Omega means this. It's the rate at which each oscillator is doing that. That's triple equal sign. That's what it means. What it's equal to, what it turns out, what we showed in all this other math that we've been worrying about for weeks, what it's determined by is the the stiffness and mass of each oscillator, or if it were a pendulum, it would be the gravitational constant and the length of the string. Like if it were a pendulum, it'd be square root of G over L. If it's air molecules, it would be something else like pressure over temperature. But the point in red, the point is that the rate at which each one of these oscillators goes back and forth is fully known in advance by whatever the materials are that make up the oscillations. In other words, fully determined by the medium. If you know the medium we're talking about, if you say it's a bunch of metal blocks on metal springs, then even before you start the process, or no matter what you do to the process, you would know in advance that each one of these things would oscillate at a certain rate. That's very important. Also, well, on the other page, okay. I mean, continue on to the other page. That letter K, okay, I'll write the equation again just so you can see what I'm talking about. Okay, the equation we're talking about is this. Right, what we just said a second ago, we said omega is defined to be 2 pi over t, that's cycling rate. But now I'm saying, what's this K business? Well, K is not, it's not the cycling rate. K was the extent to which each oscillator is out of phase from its neighbor, right? K is the rate at which we increase the phases per space in the arrangement, right? K is 2 pi, not per time, but per space. The units of K, we said, are radians per meter, right? What is this symbol here? This symbol here, lambda, you've seen in other classes, I believe, or you will have seen in other, or you saw in high school. Lambda stands for, well, it's called lambda. And what it stands for is wave length. Right? Okay, I'm trying to draw a parallel here, in a very important parallel. I'm going to try to put the two pieces of the parallel together in the next page. The parallel I'm trying to draw is that omega is cycling rate in time, is how rapidly you're doing this in time. K is cycling rate per space. Omega is how many times you do this. forth in one period, in how many cycles we undergo per unit of time. K refers us to how many cycles we could observe in a unit of space. Like, are there 2 crests per every meter as our eye gazes across this medium, right? Or are there 3 crests per every meter, or what? Omega is cycles per time. K is cycles per space. Both of them have to be occurring for this thing to be a wave, right? If you only have an oscillator going back and forth in time, that's not a wave, that's an oscillator. And if you just have a shape drawn on it, if you just have a shape with a bunch of crests and troughs, but the crests and troughs aren't cycling, aren't fluctuating up and down or flowing back and forth, that's not a wave either. That's just a picture of a wiggle, right? There must be oscillation in time and in space for this thing to be a wave. Y has to be a function of X and T. So omega is registering, is indicating, is measuring how quickly things are happening in time. K is how regularly the cycles are happening in space. Put them together and we have a wave. Just like omega is inversely related to capital T, right? Omega is inversely related to the number of seconds in a cycle, what we know as the period. Similarly, K is inversely related to what you might remember from middle school or high school or something like that, known as wavelength. Period is just the amount of seconds in a cycle. Wavelength is the number of meters in a cycle. It's literally the length of the wave, meaning the length of a given cycle of the wave, okay? So I'm just putting a bunch of terms out there. Some of them you know, some of them now you know, and I'm putting them together. But here's the punchline, and then we'll pause. Wait, I'm going to do this again. I know this is always stupid, but well, raise your hand. Okay. Raise your electronic hand. If you're probably bored, but is it clear so far? Just raise your hand if you're with me so far, if this is clear information. Okay, thank you. Okay, thank you. And thank you, Sadie. And I heard the yes, it is. I don't know where that came from, but cool. All right, I'll take it. Thank you, Amelie. Thank you, Madonna. Thank you. Okay. So if this is clear, thank you, Michael. Thank you, Roland. Thank you, Nathan. Okay. All right. So if this is clear, here's where we're now. Now we're going to take a step that we haven't taken yet. All that may be old or new, whatever. If it's clear, here's the step we're going to take with this. Hello. Okay. Okay. If we put these two things together, angular frequency over angular wave number, right? We have 2 pi over period divided by 2 pi over wavelength. So we have 2 pi over the time. We have cycles per time over cycles per space. In other words, we have space per cycle over time for a cycle. So now I'm going to ask everybody, please put in the direct chat, just to make sure we're together, in the direct chat, like as in not the public chat, in the direct chat. I'm going to wait. Could I get at least 3 responses in the direct chat for what do you get in physics when you put some kind of displacement, some kind of space interval over some kind of time interval? What do we get? What is this that we just, what is omega over k in physics terms? In the direct chat, please. Like, what is displacement divided by time in physics terms? There's a word for it. There's a number of words for it. You know it from Physics 101. Or I'll put it another way. We're awesome. That's one. Thank you. Wait. Okay. Number 1 was great. Okay. Hold on. I'll respond individually because I think it's going to take that long. Wait. Oh, yeah. So, I just got 3 responses. That's great. Hold on. I'll respond individually. Okay. I'm going to respond individually because some people need a little prompt. All right. But this is great. If you responded, then awesome. Okay. And I'm responding in order. So bear with me for a second. Hold on. Starting. Okay. I got a bunch of answers. I didn't get answers from everybody, but I got a bunch of answers. I'm going to go with them. Thank you for those of you who answered. Yes. What I'm saying is, this is some kind of velocity. If you put displacement over time, you get in physics average velocity. Or if you put distance over time, you get average speed. This is, if you put miles over hour, you get miles per hour, right? And I'm not being sarcastic. Like this is actually important. Oh, okay, good. Hold on a second. Just got more in the direct chat. Okay. I'm saying this. I'm saying this. Oops, sorry. I'm saying you could write it this way. You could write it this way, or the way most textbooks, if you take more science, I guess you won't take most of you don't take PChem, but if if you take more sciences of any kind, what you'll see in most textbooks is it written like this, all the same. Sorry, that's okay. Um, okay, the first thing I'm saying that, oh, sorry, more people came in the chat. That's good. Hold on one second. Okay. I am actually saying something here. I'm saying a couple of things. The first thing I'm saying is that if you put together those two constants in the equation, those two measurable things, omega and k, if you put them together, what you get is the amount of space for one cycle divided by the amount of time for one cycle. So what you're really talking about when you put omega over k, you're talking about v, for which v is the propagation speed of the wave. V. Now let's be very careful now. A wave is a pulse flowing from here to there through a medium that has been stretched from here to there, right? The wave is the pulse, the disturbance, the contortion of the larger medium. The medium consists of a bunch of little oscillators. Each one of these oscillators is moving all the time. Each one of these oscillators goes back to homework 1, where each oscillator at any moment has a different position, a different velocity, a different acceleration. They're moving all the time at all different kind of rates. Each one of them is going up and down in its own little neighborhood. But what that together produces is this pulse that flows from neighborhood to neighborhood, flows horizontally rather than vertical. And the rate at which this thing flows horizontally is what we call V, the propagation speed. It's fully determined by omega and k, or the way the more textbooks write it and the way we tend to use it more in problem solving is lambda and f, for which, and by the way, whenever I say f by f, I mean that thing from last homework and 2 classes ago. I mean standard frequency. The units of F or hertz. Cycles per second, in other words. Okay, so one thing I'm just saying right now is you can calculate the propagation speed of a wave by dividing omega by k or multiplying lambda by f, all the same thing. That's actually a big deal, and it's a big deal for a number of reasons. Here's the first big deal. Okay. Okay. But here's why this is like interesting. I mean, I think it's interesting and why it's useful and why we're going to do things with it. I mean, number one, I'm saying like if you know these facts, omega and K, then you know the speed at which the pulse will propagate. And again, remember, even to talk about the speed of a wave at all is like kind of a weird thing. We're talking about the speed at which a thing travels that isn't actually a thing. Like just always bear that in mind. We're talking about the speed at which a ripple flows, a certain shape flows through a medium. That's what we're talking about here. But here's what's wild. Note. Trying to get. I'm trying to get Brown. Sorry, this is. I'm sure this is not. No. Okay. There's got to be a way to get. Okay. Anyway, whatever. It's not. Um. First thing I'm saying, and okay, it really is actually important, and we're going to start solving problems with it shortly. What I'm saying is, remember the big deal. Oh, there's Sadie. Oh, hello. That's awesome. Okay, sorry. We made a big deal in the video 2 weeks ago and in class last week that the rate at which one oscillator goes back and forth is totally determined, known in advance, fixed by the material properties of that oscillator. Like the thing that I was making a big deal of 2 weeks ago is that harmonic oscillators are clocks in the deepest sense of the word. If you know how heavy your mass is and you know how stiff your spring is, you put the mass on the spring and you'll know in advance before you do anything, you'll know the rate at which it'll go tick tock, tick tock, tick tock. Remember, even if you pull the mass, if you start the mass at 15 centimeters from equilibrium, or you start it from 30 centimeters from equilibrium, if you ask the mass to make small swings in space or big swings in space, it doesn't matter. The amount of time for each swing will be the same no matter how far the swings are. This is a deep point. Again, this is how we make clocks, which measure time independent of space. It's also how we make good clocks, even in the real world, even clocks that in the real world, which have friction, which in the real world will start over time, making smaller and smaller swings, right? What we're saying is if a clock is made of a true harmonic oscillator, even if the swings get shorter in space, that still won't affect the amount of time each swing requires, right? A harmonic oscillator is a clock in the deepest sense of the word. So, okay, so where am I going with this? I'm saying each one of these oscillators that comprises the medium, like a medium is the material objects, the particles that are collected together through which a wave pulses. But the material measurable properties of the medium fully determine the rate at which each piece of the medium oscillates in its own little neighborhood. Like we already established that about harmonic oscillation 2 weeks ago. So I'm saying, wait a second. Each one of these omegas is known in advance the minute we say this is made of metal, or this is made of a bunch of air molecules through which we're going to send sound, or whatever. Once you know what the medium is through which you're going to send a wave pulse, you in advance already know or can know the rate at which each piece of the medium will do omega, and you know how far apart each piece of the medium will be, like K. They're both determined fully by the ingredients of the medium, and there's nothing you can do to mess them up. You could send really, like you could stretch the medium a lot and try to send really big ripples, really tall crests, or you could try to send really short crests, or like you did in lab 3, you could try to send a lot of crest. You could go like shake the string really rapidly and try to send a lot of ripples in a short amount of time, or you could send very few ripples in a short amount of time. No matter what you do, what I'm getting at is omega will be fixed and constant for that medium, and K will be fixed and constant for that medium. Therefore, what I'm saying is okay, this is what I'm saying. This is a big point. This is a really big point. It's a big point in English. It's going to become a big point mathematically for us for problem solving. What I'm saying, and I think this is like a physics thing, because I think if you're really following with me, as sort of ponderous and slow as all of this is, if you're following all the pieces that we've like laid out on the table, what I'm about to say now is it so logically follows from everything else I've said that it might not seem interesting, but it logically follows from everything I've said before. And yet in and of itself, at least to me, it's a total surprise. And it's not something I would have just been born knowing or expecting or even necessarily believing. What I'm saying here is this, that once you specify the medium for a wave, once you specify the medium, like you say, okay, we're going to send ripples through this long metal coil that two people are holding in the lab. Like, here's our piece of metal, here's our slinky. And like Mira's going to hold one end and Tiggy's going to hold the other, just to name two examples, or whatever. Like Yachan is going to hold one end and Roland's going to hold the other. And we're going to send ripples through this metal from Roland to Yachan, right? What I'm saying right now is I don't care, and I mean this seriously, not sarcastically. I don't care what Roland or Yachan try to do with that string. Like Roland could hold one end still, and Yachan could shake the other end a lot, like really rapidly, or he could shake it really slowly. He can make big shakes in space, or he can make small shakes in space. They can do whatever they want, but if they start sending ripples back and forth between each other with a piece of metal, like a slinky, like you did in lab 3, then those ripples can go back and forth at one and only one speed, like one constant speed, I might add, assuming that whole metal is the same metal all throughout, like assuming no tricks, like the metal doesn't get thicker on one end than the other or something like that, or the coils don't get tighter or something. If it's uniform metal, largely uniform metal from one end to the other, then no matter what we do, ripples will flow through the metal at one and only one constant speed, and we could know that speed in advance without even making the ripples. Like, so let me give another example. Like a pond, right? You drop a rock in a pond and you see the ripples coming out from that pond in the water. What I'm telling you is, as long as in advance you knew that it was water and you knew the properties of the water. So, like for metal, the properties that you might want to know are like the stiffness of the spring and the massiveness of the stuff on the metal, right? Like K over M is what you'd want to know for vibrations through an actual physical metal spring, like we studied in homework 1. If you were making a big wave out of a bunch of pendulums, you would want to know the length of each pendulum string. If you were watching ripples through water in a pond, what you'd want to know in advance, perhaps, is the depth of the water and the water pressure or the water temperature, something like that. But there'd be two material properties of the water that would be equivalent to the stiffness and the massiveness of a hook of a spring system. And as long as you knew those two material properties, then you would know the speed of the ripples in advance, and there'd be nothing you could do to affect that speed. And this is what's deep about it. And I keep saying you would know, you would know, you would know. I don't care if you actually calculate the numbers or not. I'm not saying it's not really about what we know. What I'm saying is the minute you drop a rock into the water, there's nothing the rock or anybody else can do about the speed, the velocity at which ripples will propagate, will flow through that water. They're going to flow at one and only one constant speed because each of the water molecules, because the flow is being created by individual little oscillations, vibrations of water molecules. And each one of those molecules is acting like a little bit of mass on a little spring. The reason we've studied mass spring systems for so many weeks now, the reason we've studied individual oscillation for so many weeks is because it's this fundamental and powerful ingredient to wave propagation, by virtue of which we're now believing anything that oscillates harmonically in life, a water molecule, an air molecule, a weather system, a pendulum, an electric field, anything that in life oscillates harmonically acts in every mathematical and physical way like a block of mass on a spring. And that means every oscillator in life oscillates at a frequency that is known in advance, that's fixed in advance, that's fully determined in advance by just the material physical properties of that spring. So ripples travel through the water at one and only one speed, one constant unchanging speed, as long as that water is one constant unchanging amount of water, like like one depth or something like that. I'll even, just to be more detailed or to be more fair, sure, if you're looking at, well, actually, I don't want to get into that now. I mean, if you start changing the depth of the water, you could start changing the speed of the ripples. But again, the only way we can affect or change the speed at which some waves propagate is if we play with the medium itself, if we change the medium itself. Once the medium is fixed, the propagation speed is fixed. I'm going to say the same thing because it's really that important, and you're going to see we have to start solving problems with it. Sorry. Still struggling with this 4-color thing. Sorry. Okay, I'm going to be obnoxious here just to try to wake people up. So one quick example, I have to get into the math of this now, and it does get very mathy for those people who are looking for that. But just to reinforce the point, what I'm trying to say in English again is once you identify the medium for a wave, and remember the medium is the physical collection of oscillating particles through which the wave flows. Once you identify the medium for a wave, you've in effect identified the speed at which that wave flows. Waves don't have any choice. Waves don't have any choice but to flow at a certain fixed constant speed relative to a given medium. One example that I should have just written down, I didn't. One example is just the fact that you always hear about the speed of sound. Never mind the speed of light. I mean, we'll get to that. But people always talk about like the speed of sound, right? And they just say it casually, like, oh, well, what is the speed of sound? Or, oh, that's because it beat the speed of sound. You notice no one ever says like the speed of baseballs. I mean, you could talk about the speed at which a certain baseball one day was pitched by whatever, baseball player and set a record, blah, blah. But baseballs don't go at a certain speed. Baseballs could go any speed, right? And like, it's interesting when one pitcher can throw a baseball faster than another pitcher or whatever. But people talk about the speed of sound as though there is one. Well, there is. And what they really mean when they talk about the speed of sound is they're talking about the speed at which sound pulses flow through a region of air molecules that are assumed to be at standard temperature and pressure. When people talk about the speed of sound, what they really mean is the speed of sound through air at standard temperature and pressure. But that's what they mean. But once we specify that, if you're picturing air, like at the surface of the earth, like in normal circumstances, like in New York City or whatever, and it's at basically standard temperature and basically standard pressure, then we could say in advance the rate at which sound travels through that air, because sound is a wave, because it's a ripple that consists of or is tethered to a bunch of air molecules, each vibrating at a certain rate in their neighborhood, and they only can vibrate at a certain rate. Therefore, the pulse can only propagate at a certain rate. So there is this thing called the speed of sound at standard temperature and pressure, which is approximately 340 meters per second. We're going to use it a lot in a moment. But we can rely on it. I mean, this is one of the why waves are so cool, is that they're reliable this way. But first of all, they make the physics a lot simpler, because actually, once you're talking about wave motion, you don't have to get into all this acceleration details that you spent a lot of physics 101 dealing with. There's no speeding up or slowing down in customary circumstances for a wave. They just flow at a reliable, constant speed that's known in advance. I mean, that's really powerful. And then technologically, of course, it has huge implications. One example that I want to give before we go on, though, is just to be obnoxious, is so an example of this idea that the speed of waves is constant and fixed relative to the medium is. So I always do this to my son, the one that you just, well, both of them, but the one you just met. Like if we're standing at a pond or something like that, and we're looking at, and someone throws in a rock, or there's ripples or whatever in the pond, isn't that so placid? And you're looking at ripples in a pond, I often, when my son was younger, I would ask him to let me know when he would catch one wave ripple in the act of catching up and overtaking another ripple. right? And like what I wrote here is like, remember that time when you were watching ripples in a pond and you saw one ripple catch up and pass another ripple? Well, it's an obnoxious thing for me to ask because the answer is no, you don't, and neither do I, right? I don't remember ever. And if I say to my son, could you let me know when you see one ripple catch up and pass another ripple, he'll be there all day. You never see ripples catch up and pass other ripples if you think about it, right? Like even if you're just casually watching, I'm not talking about making measurements. I'm not talking about being a scientist. You're just casually watching ripples. They always stay together, right? Like that's why they make those that's the pattern that everybody draws is a bunch of ripples in a formation. And in fact, the very idea that we can even talk about wavelength, the amount of space between the ripples as though that's a constant, right? Think about it. The fact that we even think, oh, the waves are basically 3 centimeters apart. We're assuming that they're staying that way. We're assuming that waves aren't getting closer together or farther apart as they flow. And that assumption is absolutely correct. That is what is reinforced visually by people all the time when they look and draw patterns of waves, whether they're thinking this through or not. What they're saying is whenever you don't see ripples catching up to other ripples, you're taking for granted, oh, all these ripples must be going the same speed all the time. And it doesn't matter how hard I threw the rock in. It doesn't matter if I threw a lot of rocks in. It doesn't matter if there's a lot of ripples in a small amount of space. It doesn't matter if there's a lot of ripples in a small amount of space or very few ripples in a big amount of space. That amount of space will stay constant. The speed will stay constant. In fact, I'm saying, if you start writing it the way the textbooks write it, if we say for a given wave, gosh. Okay. If we say this from now on, and this comes up a lot in other science classes, like for all waves, for any wave, right? So the speed is fixed, constant relative to the medium. So you can't change that. Therefore, right? And this is taken for granted in a lot of other. Oh, they are in the same room. You guys should study together. Okay. Right. Oh, we knew this last time. Right. Okay. No, wait, he's talking to us. Okay. I'm saying, or is he? Wait, oh my God. But how the question? But what's so weird is when the squares are like this. So then when one of them looks that way and the other looks that way, but so they're looking at each other, but there's squares on the other side of my thing. So anyway, whatever. Yeah. Oh, that's funny. Okay, that's funny. And it's even stranger that they're on mute too. So like, okay. Anyway, what is Yaverbaum talking? Okay. We need these things to keep going. We're all human beings. Okay, I think. Or are we? Wah, wah, bum, bum, bum. All right, so what I'm saying here is, I don't know what I'm saying. I'm saying V is fixed from now on. So what you can control with a wave is the frequency or the wavelength. You can make more wave ripples occur per unit time. Like again, in lab 3, you can shake your string more rapidly. So then you'll make more wave bumps, more crests, more troughs per unit time. What's the result? Necessarily, the bumps will be smaller. That's all. If frequency goes up, wavelength goes down and vice versa, because V must be fixed. That's what I'm saying so far. Now we have to get into the math of this. We have to get into something called the Doppler effect. Here, I'll do something. I'll do something next page. Whoa, hello. Okay, where I have to, and I know I am just talking and talking and talking. I'm aware of that. I have to get to a certain point of this before I can stop talking. I'll try to get to that point. I mean, yeah. I'm trying to think of a way to. Okay, yeah, I just have to keep going. I'm saying over and over again, the speed of a wave is fixed and constant relative to its medium. I have to pause now in a big way and expand on what I mean when I say the speed of something relative to something else. That's a big deal. In principle, this concept of relative speed, in principle, got established in Physics 101, although, I mean, in principle, it gets established in your first course in physics, but I actually know in my heart that it's emphasized a lot more in Physics 203, which very few of you took, than it is in Physics 101. So so I have to expand on it for a second. Well, for more than a second. Here's what I'm saying. Okay. I'm going to go on. Oh, it's still going. Okay. This may sound like a tangent, but it's not. In 1626, Galileo established a principle in a number of different ways, in a number of different languages. I mean, he wrote it first in Italian, he wrote it in Latin. In the Italian and in the Latin, he wrote it a number of different ways. We've translated them all into English. There's a number of different ways of saying this fundamental principle from which all of physics actually comes. In informal terms, the principle is it's possible for the Earth to be moving really fast all the time past the sun, and without us ever feeling it or sensing it or caring or noticing it or doing any experiments to be able to establish it at all. Like that's the idea, right? I mean, I don't want to get all off into a rabbit hole with this, which I easily could, but like before Galileo, people tended to treat the Earth as if it was still at the center of the universe, as you know. After Galileo, we tend to treat the Earth in all of our science and our reasoning and our solar system projects that we make out of fruit and tennis balls and stuff like that. We tend to regard the Earth or treat the Earth as though it's moving all the time past a sun, which in turn we regard as moving past the what's known as galactic center. We tend to, And in modern terms, we tend to believe and treat the Earth as moving past the sun at speeds of like 65,000 miles per hour, which I might add is faster than any rocket ship ever has to go in order to even get to the moon. And we tend to think of the sun as moving past the galactic center at speeds approximating 650,000 miles per hour. We now think of ourselves as standing on a rock that is hurtling through space at preposterous speeds past another object that's hurtling through space at even more preposterous speeds, and on and on and on. We think we are hurtling. Well, we learn in third grade that we're hurtling through space all the time. And in fact, we learned this from a man who's supposedly a hero for supposedly going against the supposed dogma of the church and other institutions of the time, and supposedly actually believing the evidence of his own senses and the faculties of his own logical reasoning. And we learn that Galileo is a hero for showing us that the Earth is actually not sitting still at the center of the universe, but actually moving through the universe all the time at preposterous speeds. We learn that he was a hero for going against blind dogma and advancing this view. And then we go ahead and make solar system projects out of like fruit in third grade, where we show that here's the sun and here's the Earth going past the sun. And I want to remind you that when we learn this in third grade and we start taking for granted for the rest of our life that the Earth that we're standing on is moving all the time through space at 65,000 miles an hour, we are not sensing that at all, ever, right? I mean, if I just look down at the ground, I don't see the ground doing anything uninteresting or unstable. I mean, I don't see it doing anything interesting or unstable or bizarre. And furthermore, if I jump up from the ground, I don't expect to land in a different place on the ground, right? I mean, it doesn't move out from under me. I don't think that birds have an easier time flying west than they do east or vice versa. I don't have any sense that the ground below my feet is moving, yet I've accepted the blind dogma that my third grade teacher told me, that apparently Galileo told them. I accept this idea that apparently the Earth could be moving past the sun at 65,000 miles per hour all the time without me ever sensing it at all. Why? Because what I'm really accepting from Galileo, what I'm really accepting, whether I know it or not, is a principle that he advanced in order to argue for this against the institutions that were arguing against him. Galileo's point was not the Earth is definitely moving and you definitely have to see the evidence that definitely shows that it definitely is. Galileo's point was whether the Earth would move or not, you wouldn't be able to tell the difference either way. That there wouldn't be any evidence for the Earth moving one way or the other, at least not by looking down on the Earth, there wouldn't be. Galileo's point was, and we all know this in a certain part of our brain, but we hadn't thought of it as science until Galileo came along. What Galileo told people was, look, if you go down to the bottom of a ship that's docked, and you go down into the bottom and you go to a cabin, and you look around and you make observations in that cabin and you do little experiments. Like you have a bowl of, like he literally did say this, like there's a fish bowl or something in the cabin and you watch the fish swimming around in its bowl. Or there's like a writing quill and a bunch of parchment on the desk and it's just sitting there stably. And you go near the desk and you take an object off the desk, maybe a rock, and you like drop it near the desk below your hand, and you watch as the rock falls from below your hand and it hits the ground at a point directly vertically below your hand. You just walk around, you conduct a bunch of little experiments, see what would happen, see how you're feeling, blah, blah, blah. And then Galileo said, then you can imagine where this is going. You unanchor the boat, you let the boat sail and start moving through the ocean at some high but constant speed. If you were to go down into that cabin and make all your observations again and look at the fish going around in the bowl and drop a rock from your hand and watch where it lands, you would find that all of your little observations and little experiments would work out the same way, whether the boat was docked or not. In fact, if you were in a cabin below the boat and the boat's motion were smooth and unaccelerated enough, you wouldn't even be able to know that the boat was moving. And we all know this is true, even if boats are somewhat choppy and stuff like that. We all know this is true every time we get into an elevator and and we trust that we're not going to puke on our way from like floor 4 to floor 10 or whatever like that, right? We know that once the elevator has closed the doors and has taken off and has stopped accelerating, once the elevator has gotten up to a normal speed, it feels totally normal inside the elevator. And for all we know, when the doors open, like someone has brought the 10th floor to us rather than bringing us to the 10th floor, because it feels exactly as though, right, in an elevator, the reason we're willing to take them is it feels normal. It feels like we're just standing still for most of the ride. Furthermore, you get on an airplane, right? You get on an airplane, and once the pilot comes on the thing and says, okay, we've reached a cruising speed and a cruising altitude, so it's now safe for you to like take off your seatbelts and move freely about the cabin or whatever, you know that's true. Otherwise, you wouldn't be taking I mean, you may not know why, but you know that you trust that once you're in an airplane, it feels so normal. It just feels so much like you're in a hotel room that you would have the temerity to complain that the movie in your seat in front of you is like a bad movie, or like the drink that you just got served was a bad drink, because like you're comfortable enough that you're not complaining that you're going 5,000 miles an hour through space. And you're not worried that if someone says, could you pass the peanuts? You don't go like, okay, here we go. Here come the peanuts, back up, right? You just like passing the peanuts. And if you walk to the bathroom in the plane, and if you were to jump up, you're not worried that the back of the plane will slam you in the butt. It all just feels like a hotel room, right? Why? Because not because of gravity or not because of friction or something like that. Whoa. But because in English, according to Galileo, because the laws of physics are the same at all constant velocities. The laws of physics don't change. This is Galileo's principle. Galileo's principle of relativity, form 1, the central form of it. The first thing he said, laws don't change from one velocity to another. Whatever the laws are, they're the same at 0 miles an hour as they are at 500 miles an hour. So any experiment I'm saying this, the laws are the same at all velocities. Galileo's saying this. Doesn't matter what velocity we're going, whatever the laws are the same. Just like in the United States, laws control circumstances. Circumstances don't control laws, right? So therefore, if you're on an airplane and it's like dark out, or you're on an airplane and you just woke up and you look outside and you see there's clouds moving past the plane, but you're like, wait, I don't know if I've landed yet or not. I don't know if the plane is moving past those clouds and the clouds are actually stationary, or is the plane stationary actually, and the clouds are moving in the other direction past the plane. You like, say you wake up and you don't know that. Or one of those experiences when you're in a car on the highway and like you're in traffic and you space out, and then the big truck next to you starts moving forward and you're like, oh no, did I just like take my foot off the brake or whatever? Like you see, I don't know if you've ever experienced this. I won't stop and ask if you have, but I'm sure many of you have. You're sitting on the highway, you're in traffic, there's a big truck next to you, you space out. Maybe you've never spaced out, maybe only I space out when I'm driving, but then you see the truck next to you like rolling backwards. So you think, did I release my foot from the brake? Am I going forwards, or is the truck just going backwards? And you don't know for a minute. right? You literally don't know, am I actually the one moving or am I actually still? And there's a part of you that knows that you wouldn't be able to feel the difference either way. You wouldn't. And that's not just because you're crazy. It's because of the nature of velocities and physics laws, says Galileo. Galileo says the laws are the same either way, whether you're sitting still or you're moving at any speed. So therefore, Galileo says in form number 2, therefore, there's no experiment you could ever do. There's no experiment where you could ever do to find out what's actually or absolutely going on. If you're on that airplane and you look out and you see clouds and moving, and you're like, wait, is the plane moving past the clouds? Or are the clouds actually moving past the plane? Like, what's actually going on? If you try to do any experiment in that plane at all, a simple experiment or an elaborate high-tech experiment, it doesn't matter. It doesn't matter if we haven't even thought of the technology yet. If you try to do an experiment like you say, drop a ball, I'm going to drop a ball. And I know that if I were standing in a parking lot, I know that the ball would just fall in if I were standing still and I dropped a ball, I know the ball would fall in a straight line and hit the target directly below my hand, right? It would land on a spot on the floor directly below my hand if I were standing in a parking lot. Thus, I'm going to do this experiment. I'm going to drop a ball, and if it lands directly below my hand, like if it falls in a straight vertical line and lands directly below my hand, then that must mean that I'm in a parking lot. Well, no, it must mean that I'm standing still as though I were in a parking lot and the plane is actually not moving. The clouds are actually moving. You could do that. You could make that decision, but it would be a foolhardy decision, says Galileo, because the fact is the laws are the same. Whether you're standing still in a parking lot or you're going 500 miles an hour, either way, the ball is going to land directly below your feet. Just like either way, when you walk to the bathroom and you jump up, the back of the plane doesn't slam you in the butt. So either way, the experiment will work out the same. Therefore, there is no experiment you can do to find out whether you're actually sitting still or actually moving at 1 mile an hour or actually moving at 500 miles an hour through space. So what Galileo then says in form 3, therefore, and ever since Galileo, we believe this, in form 3, Galileo says, therefore, because this is the beginning of physics as an experimental science. He's saying that there's no experiment you could ever do to find out whether something's actually moving or not. You can only find out whether, wait, hold on. Sorry. Yes. Okay. Hold on 1 second. There's just something in the direct chat. Sorry, hold on 1 second. Just happened. Wait, sorry. Okay. What Galileo says is if you can't do an experiment to find out the actual velocity of a single object through space, if all you can tell is whether one object is moving relative to another or not, all you could tell is that one object is going at a certain speed relative to another, but you can't do an experiment to find out whether one object by itself in space has any velocity or not, that since all we believe from now on in science, in physics, is what reproducible experiments tell us, then Galileo says every velocity is a relation between two objects. No velocity in the world ever is a property of a single object. From now on, what I'm saying is, and now I'm going to take this back to the wave thing. I'm saying I'm saying from now on, all velocities are comparisons between pairs of objects, that you can't really say how fast is the car going anymore in physics. You never could, it turns out. You could say how fast is the car going relative to Earth, or you could say, and that's one speed, or you could say how fast is the car going relative to this other car, and that would be a different speed. Or you could say how fast is the Earth going relative to the sun, and that would be one speed. Or you could say how fast is the Earth going relative to itself, and that would be another speed. But you always have to compare, you always have to specify two objects if you're talking about velocity. And once you specify your basis of comparison, or what we call your reference frame, that's going to affect the numerical result that you get. So now I'm going to finally get mathematical with this after all this time. So what I'm saying now, all velocities are relative. Velocity is always relative. It's always a comparison between two objects. It's never a property of a single object. It is meaningless to talk about the velocity of Earth actually. There is no actual velocity of the Earth. The Earth is going 0 miles an hour relative to itself. It's going 65,000 miles an hour relative to the sun. It's going 650,000 miles an hour relative to the galactic center. And each one of those numbers is as valid as the other. It depends what it's literally like saying, how taller is my sister? That is, I have a sister, but that's a meaningless question. You can't ask, how taller is my sister? Like literally, I'd be like, what? I have no idea what you mean. If you say, how much taller is your sister than your brother? Then I can answer. And I would lie and say a foot taller, even though she's shorter. Or you could say, how much taller is your sister than her son or her daughter? Then I can give you an answer. But you can't say, how taller is my sister? Similarly, you can't actually ask, how fast is that thing actually going? It sounds like you can. It feels like you should be able to, but you actually can't. It doesn't mean anything. No object has a velocity unto itself, because the laws of physics are the same at all velocities. Thus, mathematically, here we go. Mathematically, well, okay, well, I'll do it on the next page. So here we go for, oh, wait, sorry. Oh, I'm so glad that someone is actually paying attention to this. Wait, someone's actually saying something in the chat. Yes. Oh my God. It's such a relief that someone's saying anything, because I know I'm just talking in a mile and and I know it all seems like this has nothing to do with anything. I know that, but someone just wrote in the direct chat. I'm not going to say the name, but someone just wrote in the direct chat. This would also apply to instantaneous velocity as well, right? They were, would this also apply to instantaneous velocity as well? What a great question. First of all, that shows that you were actually paying attention to Physics 101. That's terrific. It also shows that you're paying attention to what I'm doing right now. You know, I know it's hard to do. So the answer is yes. Everything I'm saying, that is right. And truthfully, we make a much bigger deal about this in Physics 203 than in 101 for whatever reason. But the truth is, I'm saying all velocities are actually comparisons. Yes, at any given moment, at any given instant, or on average, any kind of velocity you ever talk about is actually a comparison. This is not true of accelerations, interestingly. That's a different thing. We could get into that or not. But velocities of all kinds, yes, are always comparisons. And it really is a big deal. And I'm really glad that just like someone said anything about this. I have storybooks on this I can maybe one day read we used to read them in the class if we have time. It's a little harder on Zoom, but this whole idea of like standing on a planet that we regard as going 65,000 miles an hour, and yet we feel perfectly comfortable like never feeling that. It's like a very weird idea. And all of physics, really, all of Newton's laws, everything you learned in Physics 101 and that you're learning now, it all starts with the idea of it all starts with the idea of how can we possibly believe the Earth does this without us feeling it? All of physics comes from this, all the way through Einstein in 1905. For real, I mean, if you've ever heard of Einstein and relativity and all of that, it comes from this first. I mean, Einstein added something very important to this, which you'll see by the end of the course. But it starts with Galileo, and it starts by saying velocity is so relative that we don't feel the Earth's motion, or that we wouldn't. So now I'm going to make it mathematical. But great question, direct chat person. Please submit for points for that. And in fact, if you just heard my answer, since it was way too long, if you heard my answer at all and you could just acknowledge that you heard my answer, you could submit for more points for that too. And anybody can really stop me. I know I'm just babbling, but here comes some math that'll make it more concrete, maybe. And we're going to apply to waves. We got to apply this to waves. That's where I'm going with this. So here we go. GPR, form number 4. This is the 4th form of Galileo's principle of relativity. And it has 3 cases. Case 1, one object. Oh, sorry. I have to say one thing. Sorry. Assume we have 3 distinct objects moving at 3 distinct velocities. Let the objects be called A, B, C. Oh, cool. Oh, I see that the direct chat person responded to the, all right, cool. So you could like submit for double points for that direct chat person. That's awesome. Okay. So say we have 3 objects, A, B, and C. Then we're going to do case 1 of GPR, case 1, one object. So say case 1, we're just looking at one object, object A, it's by itself. It wants to know what its velocity is, okay? Well, there's nothing else around so to compare it to, so all it can do is compare it to itself. We would write its velocity like this. We would write its velocity as velocity of A relative to A. Like from now on, what I'm trying to get at here is from now on, especially in this context of waves that we're in now, from now on, we're realizing that all velocities, something is, oh, that is so sus, Tiki. Okay. All velocities are, oh, and there's Sebastian. That's awesome. You see, I don't care, but I do care. Thank you. That's awesome. Good to see you. You can submit for tons of points for that. Okay. From now on, all velocities are comparisons between 2 objects. So we write velocities down with 2 subscripts from now on, at least in this unit of the class. We always have to have 2 subscripts to indicate what 2 objects are being compared to each other. Well, if you only have one object, all it can do is compare itself to itself. So if we have one object called A, we want to know the velocity of A relative to A. What it's always going to be is 0. This is the case 1 of, like, if you understand what I'm saying about velocities being relations, if you understand Galileo's principle of relativity, then you understand that the velocity of an object relative to itself is always 0. This is, of course, the whole like a video game concept, right? Like if you're in first person mode playing a video game, you watch the world, and this is how you experience, even if you don't play video games. I mean, I don't know how you could live, but like, no, even if you're just like in the world, visually speaking, you don't see yourself move through the world. You see the world move past you, right? And this is how movies work and everything. Like my nose is always on my face. My nose never leaves my face. I'm always here relative to me. And as I walk down 9th Avenue, what I see is all the buildings of 9th Avenue walk up past me, right? I, from my perspective, compared to myself, I am always stationary. Now, the first thing I'm saying here, this is part of the principle. This is science. This is not an illusion. This is not me being crazy. The reason video games and movies can take advantage of this concept is because it's real. To myself, I am always still. Case 2. And again, you could say like, yeah, but that's, I mean, you're just telling yourself that that's ridiculous. Well, I mean, am I? I mean, well, we'll get to that in a minute, but All right, so that's case one. Case two would be the two object case. Say we have objects A and B. Well, how does relativity, now we can do a velocity. Now we can get velocity numbers that are non-zero. Because if A and B are moving at different velocities, then A can observe B moving at some velocity, and B can observe A moving at some velocity. How do those two velocities relate? Well, again, if you've ever lived in the world or played a video game or watched a movie, you know where I'm going with this. Actually, I'm going to say the velocity of A relative to B always equals the opposite, the negative of the velocity of B relative to A, right? Like if I'm walking down, if you're standing in a building and you're on 9th Avenue and you observe me walking south on 9th Avenue at 2 miles an hour, then that means I observe the building moving north past me at 2 miles an hour, right? If I see you going to the north, you see me going to the south. If I see you going 2, you see me going 2, but in opposite directions, right? Is that fair? And what I'm trying to emphasize here is neither one of us is actually right. You could say, well, all right, but obviously the person in the building who sees the person going at 2 is more correct than the person who's looking at the building saying the building's moving. But I would say, really? I mean, isn't the person in the building attached to an Earth that's already going 65,000 miles an hour past the sun, right? Isn't that the right thing to say? And then I would say, but if you're going to say that that's right, I don't even think that's true either, because the sun is going past the galactic center at 650,000 miles an hour. So there's no actual right thing to say when it comes to velocities. That's what I'm saying. It's a matter of frame of reference or comparison. If I'm going past you at 2 miles per hour, you're going past me at negative 2 miles per hour. And now before I go to case 3, which is the one that we really need to do our wave math, note something else. Just to be clear, before I go on to the sort of meaty, hard part, to be clear, I'm saying, so whenever I write like VAB, I mean velocity of A relative to B. And the order does matter. You can see from the negative sign, the order does matter. If I say the velocity of A relative to B, I mean the velocity of A compared to B, which means the velocity that B would see or measure for A if B is treated as stationary. Now, again, when I say regarded as or treated as, I don't mean we're lying. We're not lying. We're making an assignment. Somebody is always being regarded as stationary. And whoever that is that's regarded as stationary, that's the observer from whose perspective we are measuring the world. It's always from somebody's perspective. There's no absolute, or like there's no like universe perspective. There's no outer space perspective. There is the perspective of one object or another object. So when we say VAB, we mean the velocity of A from the perspective of B. We mean B, it's like the video game thing again, which it means that B it is treated as still and seeing the world, including A, go by it. Okay, so that's the two object case. So finally, the three object case that we have to relate to our physics case. And this is all three cases of Galileo's principle of relativity. Form number 4. Case 3 is the three object case. When we have three objects, let's see. VAC will always be equal to VAB plus VBC. This is huge. This is the one that is not obvious. It's not obvious what it means. It's not obvious how to use it. It's the one we really have to use. Okay. One example of this principle is forget that. Okay, one example is like riding subways. What I'm saying is you take a subway. Why do you take subways? Because you take for granted that the velocity of the subway relative to New York City streets will add to the velocity of you relative to the subway, and thereby produce a velocity of you relative to New York City streets, right? You take the subway. Well, I can't speak for you. I take the subway because I know that I could stand still relative to the subway. The velocity of me relative to the subway could be 0. And the velocity of the subway relative to New York City streets is 50 miles per hour. 50 plus 0 equals 50. So I know that even though I'm standing still relative to the subway, I will get home because the velocity of me relative to the subway adds to the velocity of the subway relative to New York. So I thereby have a speed relative to New York, right? We take it for granted when one of the numbers involved is 0, but it's even true and also true when things get more complicated and none of the numbers is 0, or things are happening in 2 dimensions or something like that. Like you even also know, say it's on an escalator, you know that if you walk up the down escalator, that negative signs are now involved, right? You know that, or if you ever tried this in a mall when you were 5, like both of my sons certainly did, if you're in an escalator, right, and the escalator is going 20 miles an hour relative to the mall, is going up positive at 20 miles an hour relative to the mall, and then you get in the escalator and you work really hard to go 20 miles an hour down relative to the up escalator, right? Like you work really hard to run really fast down the escalator while it's going up. You know, someone standing in the mall can look at you, and you look like the Roadrunner or the Wild Coyote or something like that, with all your legs like flailing and flaying while you don't go anywhere relative to the mall. You know that 20 miles per hour of escalator relative to mall plus negative 20 miles per hour of you relative to escalator makes 0 of you relative to mall. Velocities add this way as long as they're being measured in 2 different frames of reference, right? That's what this is saying. that we can add velocities together as long as it's from two frames of reference. We have to be careful. The velocity of me relative to boat plus velocity of boat relative to water yields velocity of me relative to water. This is how the relative nature of velocities plays out once you have three objects. Now, I've been talking a lot. I recognize that, and I apologize. I have to bring this back to our way. What does any of this have to do with waves? When? Well, first of all, remember, because, well, okay, I'm saying three things here. I am watching the time, even though it seems like I'm not. Okay, so I'm tying this back. So we just did this like side, it's not really a side thing. We just did this like review of the concept of velocity being relative. And we established sort of three equations for the way that we have to talk about velocities from now on, always with two subscripts. Okay. And the reason we had to do all that is that the relative character of velocities very much applies very profoundly to the way waves move. Because number one, just to remind you, the velocity of a wave is always constant relative to its medium. If you know the and you can't have a wave without a medium. A wave is a wiggle. There's got to be something wiggling to make the wiggle. So the velocity of a wave is always constant relative to its medium. But the medium for a wave, there's no restriction. No one ever says that the medium for a wave has to be still or stationary or at rest relative to the thing that creates the wave, nor the thing that catches the wave. The transmitter of a wave, whatever kind it is, transmitter could be person in lab sending ripples along a slinky, or could be a speaker creating sound, or whatever. The transmitter of a wave does not have to be still relative to the medium of a wave, nor does the receiver of a wave necessarily have to be still relative to a wave. Thus, and tell me if you need to go back a page, thus, transmitter could be, Okay. Where I'm going with this is there's something called the Doppler effect. That's the big point here. A Doppler effect is a thing that happens with waves, only with waves. A Doppler effect is what occurs when the relative nature of velocity is applied to waves. So a Doppler effect is that thing that you all know, like you're standing on the street corner and a motorcycle goes, or like a car blaring its horn goes by you, and they're pressing the horn the same way the whole time. The person in the car hears one note coming from that horn the whole time, like but if the car's passing you, what you hear is something like right? That's the Doppler. I mean, that was very graceful, I know, but that's the Doppler effect. The Doppler effect is that specifically, and it's like very common. We experience it all the time in New York City. It may not be that interesting when we experience it with sound, but it turns out that the Doppler effect applies to any kind of waves, first and foremost sound, but ultimately and very fascinatingly light, as in the light that comes from stars, as in the Doppler effect for light ultimately tells us like really significant things about the universe, about the size, shape, and expansion of the universe. So the Doppler effect is a huge wave phenomenon. What the Doppler effect is, well, is this. Oops, sorry. Okay, I have to set up we have to start finally solving. So I have to set up a problem right now and start. We're not going to finish the problem right here. I'm going to give you case one of it. But this is what this says. So of course, so the Doppler effect, what I'm saying, the Doppler effect is what it's all about is if either the source of a wave or the receiver of a wave, and I'm including sound as a wave, sound is a wave. If the source of a wave or the receiver of a wave is not stationary relative to the medium for that wave. So if I make a sound and I'm moving through the air, or the air is moving past me, or I make a sound and you hear the sound and you are moving through the air, or the air is moving past you, if either one of us is not in the same perspective as the air, then we, the source and the receiver, will disagree. We'll measure two different frequencies for that sound, and we will both be right to ourselves, and neither one of us will be more right or wrong than the other. Note with sound waves, frequency is perceived by the human brain as pitch or note, right? So higher frequencies are higher notes, et cetera. So I'm saying if I just make a sound right now, if I do middle A on a piano, 440 hertz, and I'm just standing here and you're just standing there, you'll hear 440 hertz A. But if I'm running toward you, or you're running toward me, or the air is rushing past both of us, what you hear will not be the same thing as what I play, and we'll both be right. And we'll both be wrong. I mean, equally. This is the Doppler effect. It's differing, it's measurement differences in frequency arising from differences in velocity compared to the medium. That's what the Doppler effect is. Obviously, we have to start doing numerical examples of it, and that's what we'll do. And I'm sorry, I am aware of I can't get, I know people, I can't give a break today because I have to finish this. I will owe you you remind me at some point when we're a little bit more casual that I'll give you an extra break or something like that. I mean, obviously you have to go do what you have to do, but I have to finish explaining this before the class ends at 5:45. So forgive me. And we have to talk about something logistical too, but well, I'm not going to. So anyway, the Doppler effect problems can be classified into 4 basic cases. And we're going to set up one of them right now. We're not going to do all 4, but the 4 basic cases are like, well, okay, receiver approaching, receiver receding. It doesn't matter what the order of the cases, but and source approach, source recede, if you see what I'm saying. The 4 basic cases are the 4 options, like the receiver goes away, or the receiver comes in, or the source goes away, or the source comes in. But any of those cases, there will be a Doppler effect. And the Doppler effect is the source and the receiver disagreeing on the frequency of the wave sent, or specifically in the case of sound, they'll disagree on the note that they hear. And if they both made tape recordings or whatever, and then got together later on and played the 2 tape recordings, the 2 tape recordings would be different. And neither one is like more correct. It's a relativity thing. So source. So I am aware of the time. I'm going to set up one case right now, ideally solve it, but I'm not going to do all 4 cases. So here's a case of the Doppler effect. In fact, this is technically your homework, so I'll use literally the numbers from your homework. So I'll set up the first case, and then I'll promise you this. The rest of the cases work by the exact same method. You'll get different answers, but they all work by the same method. So I'm looking at, so this is a homework that's due next week. I'm looking at it right now. I'm not going to put it on the screen, but so you have, I don't know why it says Wiebelfetzer, but so you have a source. So you have like a speaker. Sorry. And it's making sound. And then you have like an ear, somebody listening to this sound. Okay, so this is like the source. And this is the receiver. Again, for anybody who's still paying attention, I can't imagine how you would be. But I'm starting your homework for you. I'm going to show you what you're doing for this homework that's due next week. It asks you to analyze 4 different cases and get 4 different answers or something. If you do the procedure that I'm about to do in the next 11 minutes, you do the exact same procedure, exact. same procedure for each case. And if you do it right, you'll get different answers, but you'll do the same thing. So here's the givens. The given is that this is a sound, so the velocity of the wave. Okay, so now everything has the two subscripts, right? Like we're going to use, this is all about using those Galileo's principle of relativity with all the subscripts. So we're saying W stands for wave, M stands for medium, S stands for source, in other words, the speaker, if this is sound, and R stands for receiver. So what's given? Well, what's given is the velocity of this wave relative to, I'll do a different color. What can be given here is the velocity of the wave relative to the medium. That can be given because that's what's always fixed. What we know about, for example, sound is it always will go 340 meters per second relative to its medium, relative to the medium, which is air. The medium is air in the case of sound. What's also given in this problem is we say, all right, okay. So let's say in this case, the velocity of the receiver, let's say, is moving towards the medium at 80 meters per second. This is one case. So I'm saying, say the receiver is moving toward the speaker at 80 meters per second. And to make things really, really clear, let's say that the direction of the wave goes is positive, and the direction against the wave is negative. So the velocity of the receiver is moving towards the speaker at negative 80 meters per second. The velocity of the speaker is not moving at all. The velocity of the source relative to the medium is 0. Again, I'm just using the numbers from the sheet. You could look at this later and you'll see I'm just taking the numbers from the homework sheet. But the homework sheet is like vague as to which numbers apply to which, because the homework sheet is asking me to do each case one at a time. So in this case 1, I'm saying the receiver is moving toward the source at 80. The source is just sitting still. The sound is coming out of the source at 340. And the last fact that is given to me in this problem is that the frequency of the wave relative to the source is 800 hertz. That's a realistic number. That means it's like higher than, that means it's a little bit flatter than on a piano. It's like an octave up from the middle A, but a little flatter than that. So maybe it's like the G right before. Anyway, it doesn't matter. It's a realistic note that could be found on a piano. So our goal, again, I know I'm going a little fast now with only 8 minutes left. I'm just showing you how to do this to solve these Doppler effect problems. These are the givens. The question, what is the question? Is given all of the above, what is the frequency of this wave according to the receiver? That's what I'm trying to figure out, because that's always what I'm trying to figure out in any Doppler effect problem. You know the frequency according to the source. You're trying to figure out the frequency according to the receiver. They will always be different if it is a Doppler effect problem, which this is. So how do you do it? How do you figure out? There's a procedure that I'm going to tell you right now in these 7 minutes. You're going to follow this procedure for every one of these cases. The procedure, the Doppler effect procedure, is to use all the facts that we were taught in this class today. The Doppler effect problem-solving procedure. I mean, still embed this into your 5-step method, obviously, but one, or like step A, what I always do is solve for the wavelength of the wave according to the source. I'm telling you this right now for those people who are still, I know we have 6 minutes. But this is like the meat. Everything I just did in the whole class, I know it was long. It was all pieces that I had to put on the table so that we could put them together and solve this kind of problem. Like, and I know I'm going fast now, but this is the point of all of that stuff. It's all gonna. So what I want to ask was 6 minutes. Sorry. Are you still with me with it? Like, oh, she's looking really upset. Oh my God. Wait, are you still with me for the, yeah. Okay. Fine. All right, cool. Fine. Okay. So I'm just telling you, this is what you do. Like, I think it's logical. I think you'll see it. Oh, thank you, Madonna. Awesome. Thank you all. Okay. So I'm yelling, I'm going fast, but this procedure that I'm telling you, when you sit down and try to do the homework or with each other, whatever, you'll hopefully see that the procedure makes sense. I'm not just making it up, but here's what it is. First, I always solve for the wavelength according to the source. How do I do that? I go back to the fundamental from the beginning of this class. I know that velocity of anything, of any wave, is wavelength times frequency. Now I'm just putting in subscripts now. Like the first part of today's class was establishing that for a wave, V equals lambda F. Okay, the second part of today's class was establishing that all these V's and all these things that we're saying actually have to have two subscripts on them because everything's actually a comparison. So I'm applying okay, so if you look back in your notes later, you'll see I'm saying V equals lambda F, like for any wave. We established that at the beginning of the V equals lambda F. So the velocity of the wave according to source equals the wavelength of the wave according to source times the frequency of the wave according to source. I'm just being consistent. And why am I doing that? To rewrite it and solve. I'm solving for wavelength according to source. So it's going to be VWS over FWS. I'm going to the next page now. So VWS equals, I'm sorry, I mean lambda WS equals VWS over FWS. I'm just using consistent subscripts. Why S? Because that's the first step, is I always measure the wavelength according to the source first, because I can. So what's the velocity of the wave according to S? Well, I wasn't technically given it. I wasn't technically like, so what's VS? Like I'm going to plug in now, right? What is VS? I don't know technically. It wasn't told to me. But from Galileo's principle of relativity, form number 4, case number 3, I know that VS must be equal to VWS must be equal to VWM plus VMS. Just look back on the ABC arrangement from there. Velocity of me relative to subway plus subway relative to streets equals me relative to streets. So I can use this. I know that, and I'm going fast again, you'll see it in your notes when you look, but VMS means velocity of the medium according to the source. That's 0. If you look at the givens in the problem, that's 0. So VWS equals, in other words, the velocity of the wave according to the source is the same as the velocity of the wave according to the medium, which is 340 meters per second. So for this one step, I have an easy time. I could say the wavelength according to the source equals 340 meters per second over that given 800 hertz. So I put that in. There's only 2 more steps to this procedure. I know that there's 3 minutes left, but there's only 2 steps, I promise. And the second one is really fast. Okay, so bear with me. And if you have to go, you go. And I'll, I'm just going to keep talking until I finish this, and then I'll upload the notes. But so 340 over 800 tells me that the wavelength of the wave according to the source is 0.425 meters. That is step 1. Why did I just do that? Because now step 2 of the 3-step procedure, step 2 is I say to myself, I got the wavelength at the source, because if there's one thing I know is the wavelength is going to be constant. The wavelength of the wave according to the receiver necessarily will be the wavelength of the wave according to the source. That's that whole concept of the ripples in the pond. Like they're traveling from the source to the receiver. Everybody's going to agree on how far apart those ripples are. There's nothing anybody can do to mess with that. So I can now, I got the wavelength according to the source because I know in advance it will be the same. It's the one thing that will be invariant in this whole scenario, that the wavelength according to the source must be the same as measured by the receiver. So I can now go to the third and final step. I could say, oh, then I'm going to go to the receiver and I'm going to solve for the frequency according to the receiver must be the velocity of the wave according to the receiver divided by the wavelength of the wave according to the receiver. I'm literally just doing what I did in step 1 and inverting it. Like, again, we have 1 minute left. In step 1, I use frequency to get wavelength. Now, in step 3, I'm using wavelength to get frequency. Why is that not a circle? Why is that going to get me any knowledge at all? Because VWR is the key. The velocity of the wave, according to the receiver, and we're just about done, I promise. The velocity of the wave, according to the receiver, is not known. It's not 340. 340 is the speed of sound through the air. That's what's known. And yeah, the source is just sitting in the air. So the source agrees with that speed of sound. But the receiver is running through the air. Therefore, the air is going past the receiver. The receiver is not experiencing the same speed of sound as is the air or the source. That's the key to this whole thing. The velocity of the wave according to the receiver, I must use relativity. It must be velocity of wave according to medium plus medium according to receiver. We're just about done, I swear. You're being very patient and very kind. What's the velocity of the medium according to the receiver? I don't know. Nobody told me, but somebody told me in the problem that the velocity of the receiver according to the medium was -80. Therefore, see, this is all relativity. That's why we had to, okay. Therefore, the velocity of the medium relative to the receiver must be the negative of -80. In other words, the receiver sees the air rushing toward it at 80 meters per second. So we're 2 lines from done. And if you have to go, you have to go, but I swear I'm just about done. Therefore, the velocity of the wave relative to the receiver must equal the velocity of the wave according to the medium plus the velocity of the medium according to the receiver. So it must be 340 plus 80. The receiver experiences the wave as traveling at 420 meters per second. Not the speed, higher than the speed of sound, because the speed of sound is what the wave does to the air. But this air is moving according to the receiver because the receiver is moving through it. So last line, literally last line. Therefore, the frequency of the wave as according to the receiver must be this 400 is this velocity of the wave according to receiver over the wavelength of the wave according to the receiver. So it's 420 meters per second over that number that we originally got, the 0.425, over 0.425 meters. So the frequency of the wave according to the receiver, this is the answer, and this is done. I mean, and we're done. And thank you for being so patient and indulgent. And it is 988 hertz. In other words, the source sent out like a middle A, but the receiver heard an A sharp, so to speak. The receiver got a note that was higher than the source sent because the receiver was running into the sound waves as he or she experienced them. That's the end. Okay, that's a lot. We're 2 minutes over. You can go. So thank you for being so patient. I will hang out and answer any questions. And I'll say this too. I'm not saying this to be a tease. You could definitely go. But I know that the issue of exams is on people's mind and people are worrying about that or wondering. So I will be giving you more information about that shortly through Google Classroom. But if you want to stay and hang out for a second and have any influence over that, you can do that. I don't mean that as a, but we do have different exams soon. It will, so you can hang out for a second to hear more details if you want. But other than that, I'll put the information in Google Classroom and I'm going to talk to your lab instructor. But okay, that was a very obnoxious thing to say right at the end, but I know it's on people's mind. So thank you. Hold on. I'm going to stop the recording too. Hold on.